All right, we're going to continue looking at some momentum calculations and examples. Recall that we have this relationship for impulse, J is equal to the integral f dt, impulse approximation, f average times delta t, but in either case it's equal to the change in momentum, mv final minus mv initial. Now, in the special case where the f external is equal to 0, we have the sum of the initial momentum equals the sum of the final momentum. And this is a vector sum called conservation of momentum. So let's take a look at a problem up here, a skateboarder. We have with a 40 kilogram mass and a 5 kilogram weight, it looks like there. You can imagine it's a physics text if you want to think of something that you might want to throw away in disgust. So here's our skateboarder. And the skateboard has a mass of 3 kilograms. The physics text, or the weight, whatever, is 5 kilograms. It's a pretty heavy book. And she has a mass of 40 kilograms. So the initial momentum before she throws the book is 0. So that's the sum of P naught is 0 because nothing's moving before the interaction. But then she throws the book, and now the book is moving with a velocity v2, we can call it here, equal to -7 meters per second. Now, the reason why we're calling that negative is somewhat arbitrary, but she then is going to be recoiling and moving in the opposite direction with some velocity v final. Okay, so the sum of the final momenta has to also be equal to 0 because there are no external forces here. All of the forces in the system are forces of her on the book, but force of the book back on her, pushing her in the opposite direction. So for P final here, we're going to have M2 V2, and we're going to have for her M1 V1. Okay, or V final, we could call it here, M1 times V final. And so that also has to add up to 0. Okay, so if we define the positive direction to be to the right, then we have 0 for the initial momentum equals M1 V final minus M2 V2, like that. So that those two momentum vectors, which indicate the final momentum of the system, are still 0. So we start out with 0, we end up with 0, but in the process of writing 0 here, because these two vectors, these two momentum vectors are canceling each other out, we can then solve this for V final. So this gives us V final equals M2 over M1 times V2. Okay. And so we got the negative sign from the fact that V2 is what we could call in the negative direction. And so M2 then is the mass of the book, so that's going to be 5 kilograms divided by M1. So let's look here. Can we see what M1 is? Is it 40 kilograms? Or is it 43? It's 43 because she is the part of the system that's moving, what we could call here M1, is her with the skateboard. Okay? And so that's going to be 43 kilograms times 7 meters per second. Okay, so that then gives us an expression for the final velocity. It's going to be a lot less than the velocity of the book. Okay, so here we have basically M2, V2. Here we have M1, V final. Okay, so it's a small mass times a big velocity. In this case equals a big mass times a small velocity. So we knock this number out, and we're going to get a small fraction of 7 meters per second. So here it's just going to be 0.814 meters per second. As her final velocity, her and the skateboard moving in the opposite direction. Let's look at another example of conservation of momentum. Here we have an astronaut. Now you'd think that he would already know physics, but apparently he forgot something that he needs while he's on his spacewalk, so they throw him the physics book. Okay, and so the physics book, let's say, is moving toward him at 4 meters per second. It's a 3 kilogram book, and then he catches it. So let's find his final velocity after he catches the book. Right, so this is our initial momentum then. It's not 0 in this case because initially before the collision, the 3 kilogram book is moving with a velocity of 4 meters per second. And so then the astronaut has an initial velocity of 0, but then after the collision, the book and the astronaut are moving with a velocity v final. And so this is going to be M1 plus M2 times V final. Whereas here, this is just M1 times V1 initial plus M2 times 0. So this is our initial momentum, small mass times a relatively big velocity. After we catch it, bigger mass times a smaller velocity. So solving this for V final, we get V final is equal to M1 divided by M1 plus M2 times V1 initial. Okay, so this is 3 for M1, and then afterward, the M2 is going to be 63. So this is 3 kilograms divided by 3 plus 60 kilograms times V1 initial. That times 4 meters per second is 0.19 meters per second. Okay, so we can show here, if we wanted to, that energy is not conserved during this collision, this inelastic collision, and that some energy has been turned into heat. We could find that by finding the final kinetic energy and the initial kinetic energy and subtracting them to get the difference in kinetic energy. But remember that the momentum equation works regardless of how much energy is lost. Even in that other example that we looked at, the ballistic pendulum, where we lost 99.9% of the energy, we still have the initial momentum equals the final momentum. And so that's the way to proceed. in these kind of problems. Here's another example I wanted to look at. Let's say that we have a bullet that's fired through a metal plate. So let's say the metal plate is sitting here maybe on a table or something. And the metal plate has a big mass, m, is equal to 1 kilogram. We have a little bullet that is moving with a velocity of 1,000 meters per second and is just a 10-gram bullet. It goes through the mass, and then after it's gone through the mass, it has a final velocity of half of its original velocity. So V1 final then for the bullet is 500 meters per second, whereas initially, before it went through the plate, it had a velocity of 1,000 meters per second. Let's assume it still has the same mass, and that the plate hasn't lost any mass by knocking the hole in it, okay, because it's a small hole. So let's find V final for the plate. Okay, so the plate then is going to feel the force of the bullet penetrating it and going right through it, but then that's going to allow the plate to pick up some of the momentum that the bullet lost, because that's the only other place for it to go. And so if the bullet has lost half its momentum, is it still has the same mass, but half the velocity, that means that that amount of momentum must have been given to the plate. And so that is the way that I would physically look at the problem. The sum of the initial momenta in this case is just going to be the mass of the bullet times the velocity of the bullet, plus the mass of the plate times 0, because initially it's sitting on a table or something, or it could be in space too. It's just suspended there somehow. Then afterward, it's going to have a velocity just after the collision. So that's going to be equal to mass of the bullet. That's not a common velocity anymore, because the bullet has dropped from 1,000 to 500 meters per second, but then plus the mass of the plate times V final. Okay, so this term is 0. That's relatively simple setup here. Really, once you've got the equation written, the algebra isn't bad. The mass here would be 10 to the minus 2 kilograms, which is 10 grams. 1 gram is 10 to the minus 3 kilograms, so 10 grams is 10 to the minus 2. So here we have 10 to the minus 2 kilograms times 1,000 meters per second equals 10 to the minus 2 kilograms times 500 meters per second, plus the mass of the plate, which is 1 kilogram times V final. Okay, so if we solve this for V final, we get that V final is equal to 10 to the minus 2 times, well, here we have 10 to the minus 2 times 500, 10 to the minus 2 times 1,000. So if I subtract these, this would be 10 to the minus 2 times 500 divided by 1. Okay, so that would be then, this would be 1/100th times 5, would be 5 meters per second. So that would be the velocity of the plate. Right, so these are all examples then of problems in which we can figure out the final momentum from the initial momentum in a one-dimensional problem. And now I'm going to expand this to two-dimensional conservation of momentum in a little while. But before I do that, I'd like to look at a couple more examples of just impulse equals change in momentum that are useful in getting accustomed to the concepts of how to work with these equations. Now if we want to look up at the data projector for a second, we can see here that you can do amazing things with the principles of impulse and momentum. You can break huge pieces of brick with your bare hands. And it seems like these kinds of feats are almost superhuman, but no, it's not magic, it's just physics. And so the way that we could imagine this is to think in terms of the average force that's acting and the amount of time over which the force acts. And remember that that's equal to mv final minus mv initial. Okay, so what if you were trying to impart a huge force to that brick? And if you plotted the average force versus the time, basically, or the force versus the time, and we have an average force associated with that. You wanted to make the area under the curve peaked out as much as possible, then you'd want to have a small delta t. In other words, for the force to be big, you need a small delta t. Okay? And so what you're trying to do then in karate is to deliver your force in a smaller length of time. Okay? And so let's compare that to what you get, say, if you don't hit it hard. If you don't hit that brick hard and it doesn't yield, then you break your hand. Why did that happen? Because you spread the force out over too much time. Looks like that, F versus T. It still has the same, let's say, the same area under the curve as before. Let's assume that that area is the same as this area. You can make this look a little more to scale by doing that, so that this area is the same as this area. But here we have a small force and a big delta t. Okay? And so in this case then the brick doesn't break. But your hand breaks. Whereas here, with a large force over a small time, the brick breaks. Okay, now, what is the mv final, mv initial here? This is just the mass times velocity of your hand after minus the mass times velocity of your hand before. Okay, and so that difference in momentum is how much momentum you've been able to deliver to the brick. That gives rise to the larger force. And so let's say that you're walking along, you've learned the principles of karate, and then you're this little 100-pound person, and these 5 guys try to beat you up. And so all of a sudden, bap, 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 and they're all laying on the ground, writhing in agony. Is it magic? No, again, it's just physics. All a black belt has to do is deliver that force in a smaller length of time. And so how do you do that, though? And by the way, a lot of black belts don't know that this is what they're doing. They just learned the technique. They haven't learned the physics behind it. But let's say that this is your target right here. And so I'm trying to deliver the largest possible force with the momentum of my arm that I can deliver. And so what I do then, if I'm trying to minimize the amount of time that it takes to deliver the momentum, is I don't focus here. This isn't my target. My target is way back here, a meter behind this object, so that you hit it, you drive through, and you let the inertia of the object help slow your hand down faster, so that your time of contact is lower. That's what gives rise to the big bap, and the person is knocked unconscious. Okay, so you can make yourself 5 times stronger, essentially in terms of the force of the hit, if you can deliver the momentum 5 times faster. And so that's the technique that is used with karate. But there are many situations where you wouldn't want to have a big force. Say, if you're in a car accident, then you don't want a big force. And so that's when you want to stretch the time out. That's what the airbag does in your car. Instead of you slowing down exactly at the same rate that the car slows down, what you do is you compress into the airbag, and that expands your time of contact, and it allows for the force to be reduced to the point, because it's basically force through time. So it's less force through a bigger time, or more force through a smaller time. It still gives you the same change in momentum. Okay? But you can use this kind of a strategy then with a padded dashboard or with an airbag or whatever to minimize your injuries during a collision. Now, let's say in the next example, we have a force versus time function that looks like the following. Say that the force peaks out some value, then drops off again over a length of time that's equal to, let's call this 0.1 seconds, and this 0.2 seconds. And let's say that this is the force of the ground on the ball. So that force then is a time-dependent force as this ball falls through this height and then interacts with the ground, and that ground then causes the ball to be projected upward at some higher velocity. Okay, so let's say the ball starts at 2 meters high, strikes the ground, over this 0.1 second time interval, and then rises up to a height of 3 meters. So we've had inelastic collisions, we've had elastic collisions where no energy is lost. This would be called a superelastic collision, because here you have more energy afterward than you did before. You start out at 2 meters, the thing drops down, and then this is the force function as a function of time in this 0.1 second time interval over which the mass is in contact with the ground. And then at the end, it pops up to this height of 3 meters above where it started from. And so from this information, let's find F max for our force function. So that's going to be the maximum value of the force of the ground on the system. All right. So what we need to do then is set this up, because there is an external force now. So we're not just using conservation of momentum. We're saying impulse equals change in momentum. So we can say then that the integral of F dt is equal to mv final. So this is just after the ball loses contact with the ground. That's going to be our v final there, minus mv initial, where v initial is going to be the velocity of the ball just before it hits the surface where the force is acting. So this gives it a little extra momentum. In other words, this is the force function here is a source for the momentum that makes mv final larger than mv initial. And so we could figure out what the slope is of these two curves, and write this as a function that has two different domains. or we can just find the area under the curve. And so the area under the curve then is going to be 1/2 base times the height. So that's going to be our impulse. So this is an example of where it's easier for us to work in terms of the area under the curve rather than actually performing the integral. This is going to be 1/2 times the base, so that's 0.1. So that's the delta t in this case is 0.1 times the height, which is F max. Okay, so that's our area under the curve. And so now what we need to do is figure out what V initial is just before it hits the ground. We can get that from V squared equals 0 squared plus 2ay. Okay, so this is for the way down. So this is the final velocity for the way down, but it's the initial velocity for our momentum calculation. So I'll just call it V with the feet on it there. Okay, but it's this velocity here that we're looking at. So that velocity then would be the square root of 2 times 10 times 2, as it's dropped through 2 meters. So that gives us the square root of 40. Or 6.32 meters per second. Okay. And we will need the mass of this thing too. Let's make this a 1 kilogram object so we don't have to worry about a lot of other numbers. Okay, so that's going to be this velocity. Now the velocity just after the collision, or the interaction of the ground, which has this force function, with the ball, is going to be, well, by the time it gets up to here, it'll be 0 squared equals the velocity at the bottom plus 2a times 3 meters. Okay, so it goes up higher than it started from. So that means that V after the collision is going to equal square root of 2 times 10 times 3, or the square root of 60. And so that gives us 7.7 meters per second. So the extra momentum that we've gotten in this problem then is going to be equal to 1 kilogram times V final, which is 7.7 meters per second, minus 1 kilogram times 6.32 meters per second. And we'll set that equal to this quantity here, which is 1/2 times 0.1 times F max. Okay. So this is our equation then. And so just reviewing what we've done so far, because the rest is just algebra, is we've said that using the impulse actually finding the area under the curve, I should say here, is equivalent to performing the integral. So we did that knowing that the triangle's area is 1/2 the base times the height. And so that isolates everything in terms of F max, which is what we want to solve for. And that's the difference in our momentum. Okay, now here we have to be careful because this momentum vector is pointed down and this one's pointed up. So this is actually a negative value here. The 6.32 is negative if we call the force direction the positive direction. So really this should have been given a negative sign because the ball has to go all the way to 0 and then from 6.32, then all the way back up to 7.7. So this is minus a negative there. And so that's an easy place to make a mistake. So once we have all of that in place, This is the change in the momentum of the ball. If we're perfectly elastic, it'd be going the same speed on its way back up. But because the force function added a little momentum, it has a little greater speed on its way back up. And so that change in momentum then is equal to the area under the curve. Or finally, that gives us F max equals 7.7 minus 6.32 divided by 1/2 times 0.1. So that gives us 28.5 newtons. That's the maximum force in this variable force problem, and that is the force that is required by the ground to be applied to the mass, so that if it starts at 2 meters high, it will bounce back up to a height of 3 meters high.